one terminology called switching threshold voltage denoted by Vm is defined as the point where V in equals to V out. Its value can be obtained graphically from the intersection of the VTC with the line given by V in by V out. It simply means that suppose this is your VTC, something like this is your VTC, and V in equals to V out plot is this. This plot is V in equals to V out. So the intersecting point is this one. This is called GM, switching threshold voltage of inverter. GM of inverter. We are talking about inverter now, static behavior of CMOS inverter. Okay. And VM can be calculated as this equation by equating the current. See, inverter, once you are considering the amount of current passing through the N MOSFET is equal to the P MOSFET. So equating inverse currents and using this equation, you can obtain the value of VM with R equals to Kp Vd sat P by Kn Vd sat N, which can be also written as V sat P. This is not actually V, it is new sat P indeed. Wp by nu sat N Wn. This also can be written if you assume that oxide thickness for P MOSFET and N MOSFET are equal. In that case, you can write this one also. This is the definition of switching threshold voltage, and it is one of the design metrics, important design metrics of inverter. Once you try to design an inverter, CMOS inverter, then you should try VM should be VDD by 2. Okay, for that you have to properly size the MOSFET so that R becomes 1. If R equals to 1, then it is VM equals to VD by 2. Do you understand this? From this equation, VM equals to R VDD by 1 plus R. R is already defined here in this equation 5.3. You'll get VM equals to VD by 2, and it should be located around the middle of the supply voltage. Suppose supply voltage in 250 nanometer technology generation is 2.5 volt. So VM ideally should be 1.5 volt. Why? Because with this you can maximize the noise margin. Means you are aware of noise margin. One is called NML, another one is NMH. Low noise margin and then high noise margin. You are aware about the definition, so we will not discuss this thing. Now, if VM is less than VDD or more than VDD, then we call that inverter as unskewed inverter. To move the VM upwards, a larger value of R is required in that equation, which means making the P MOSFET wider, increasing the strength of the N MOSFET. On the other hand, moves the switching threshold closer to ground. Okay. See, ideally, as I said, should be at the middle of the, say, your this VTC depends on the width strength ratio of N MOSFET and P MOSFET. If your P MOSFET is stronger, then N MOSFET will take longer time to pull it down. So VM will move up in this direction. Okay, in this direction. So to make the VM equal to VD by 2, what is needed? The strength of N MOSFET should be equal to strength of P MOSFET. Okay, that is this should be 1. This should be 1. W by L of P MOSFET divided by W by L of N MOSFET, which can be obtained from this equation, current equation of the inverter, I mean N MOSFET and P MOSFET. You can obtain it once it is VM equals, I mean ratio, strength ratio is equal 1, then it will lie in the middle of the VDD. The VM equation is written once again here as VTN plus R within parenthesis VD plus VTP by 1 plus R, with R equals to square root of minus Kp by Kn, where Kn is the W by L beta gain factor, and process transconductors parameter is given is this. We have said also earlier. So when PMOS and NMOS are long channel devices, or when the supply voltage is low, the velocity saturation does not occur. Velocity saturation when occurs, what happens? Your VD SAT, VD saturation velocity, is less than VGS minus VT. Means before pinch off, normally we have seen that VDS should be greater than equals to VGS minus VT in long channel MOSFET. VTN. Long channel MOSFET, this is the condition. I mean, should be greater than equals. VDS should be greater than equals in long channel MOSFET. But we have seen that due to carrier velocity saturation at lower VDS saturation occurs. So that in that case, velocity saturated MOSFET, this condition prevails. VD sat, the VDS at which saturation occurs is less than VGS minus VT. Okay, and we know that for that current will be less also. So this is the equation or condition rather. Velocity saturation does not occur, so VM minus VT less than VD sat. Under these circumstances, VM will be this, and all parameters are known to you, Kp, Kn, etc. So for maximizing the noise margins, what you need to do is the sizing of the N MOSFET and P MOSFET has to be done. When designing static CMOS inverter, it is advisable to balance the driving strengths of the transistors by making the PMOS section wider than NMOS section. If one wants to maximize the noise margins and obtain symmetrical characteristics, the required ratio is given by this. This is in the form of equation. If you want to simulate, then also you can try, but you will see that width of PMOSFET will be larger required. Okay, 2 to 3 times wider. It should be 2 to 3 times wider. Then only, I mean, it can match up with the strength of N MOSFET. Because of mobility of electron is higher than hole, 2 to 3 times higher. That's why it happens. Here is one example. We derive the size of PMOS and NMOS transistors as that the switching threshold VM of a CMOS inverter implemented in our means the book is written at 0.25 micrometer CMOS process based, hence is talking about this is located in the middle between the supply rails, means VD 2.5 volt and ground. It will be At the middle, that is 1.25 volt, we use the process parameters presented in this table and assume a supply voltage of this. The minimum size device has a width oblique length ratio. Minimum size means channel length might have been taken the minimum of this technology. In this technology, 2.25 micrometer, which is equivalent to, you can say otherwise, 250 nanometer, all the same. So at this technology generation, the supply voltage normally is 2.5 volt, and it has been found. So minimum channel length will be 250 nanometer. You cannot reduce less than that. Okay, then your simulator also will not work. So minimum size device is telling minimum size device. The minimum size device has a width over length ratio 1.5. Means a length, if you have taken 250 nanometer, width multiplied by 1.5 means 2.5 in 250 nanometer into 1.5. This is the width, okay, taken, and the result has been obtained. Parameter for this technology generation is N MOSFET VT is 0.43 volt, P MOSFETs minus 0.4 volt, and gamma is given here as 0.4 minus 0.4. VD SAT is 0.63 and minus 1, and K prime is given as this, and for N MOSFET, and this one is P MOSFET, lambda is 0.06 and minus 0.16. So using these parameters, it has been simulated for VM equals to VD by 2, that is 1.5 volt. Here is a plot, VM versus WP by WN, that strength ratio, width ratio of P MOSFET and N MOSFET. And what is the conclusion of this is here, the simulated PMOS NMOS ratio of 3.4 for a 1.25 switching threshold conforms. I mean, if you make the width ratio WP by WN equals to 3.4, say this is 1, say 2, 3, 4. I think possibly this is the 4. So somewhere here, if you go up, then what you get is the, for a switching threshold of 1.25. So 1.2, 1.25 somewhere here. Okay. So this is what is telling. To obtain the VM equals to VDD by 2, 2.5 divided by 2 equal 1.5, sorry, 1.25. What is the strength ratio required? Sorry, width over length, width over width ratio. WP by WN is this much, 3.4. Why it is required? Because of the what? Prajwal, why is not one?
The larger mobility of pulse.
Larger mobility, very good. For the above example, setting the ratio of 3, ratio to 3, 2.5 and 2, L switching threshold of 1.25, 1.8. See the values. The ratio 3, 2.5 and 2. Got a change, a lot of change in the ratio, but you see the switching threshold is not changing that much. 1.25, 1.18 and 1.13 volt respectively. changing the threshold voltage with width ratio is not so easy. Means quite, I mean, higher ratio is required to make a change. That's what is meaning. Now, inverters can be three types. One is called unskewed inverter if WP by WN, or in other words, you can say strength ratio. Better to say strength ratio. Beta P by beta N. You can say beta P by beta N. Beta means mu P, mu P C ox W by L is the beta, and here mu N C ox W by L. This W by L of the MOSFET, this W by L of N MOSFET. So if this ratio is 1, then we call unskewed inverter. Unskewed inverter. If this is less than 1, see, say 0.1 is given here, then your VTC will be following this one. If this beta P by beta N less than 1, then we called what? Low skewed inverter. Low skewed W is there. Low skewed inverter. And if it is greater than 1, then we call high skewed, HI, high skewed inverter. Okay. So can you remember these things? You must remember. So it is very easy. We'll go ahead fast. And by this Sunday, we should finish this and conduct the quiz one. Sometimes, asymmetrical, this is a case of asymmetrical, this one as well as this one. Symmetrical is this one, when your beta P by beta N equals to 1. That is symmetrical. Your rise time and fall time will be same. Charging of the CL will take equal time when you will discharge it. Discharging time required will be same, because current passing through N MOSFET as well as P MOSFET will be same. Strength ratio is same. Okay. So that is mostly desirable, but sometimes unskewed inverter is also useful, as has been shown here. The input is here, your output ideally, if you have Vm equals to say VDD by 2, in that case your output will be inverse replica of the input. Okay, but that is not sometimes desirable. In that case, if you make the inverter skewed, then it will be better. Can somebody say, in this case, if this is the output, then it is skewed, but what skewed? Low skewed or high skewed? Think up and tell. Passing this signal through a symmetrical inverter would lead to erroneous values as shown in A. This is A. This can be addressed by raising the threshold of the inverter. Switching threshold of the inverter, which results in a correct response. So it is what one? Tell me.
High skewed.
High skewed inverter. Anyway, going further. However, altering Vm by a considerable amount is not easy. We have already said that. Especially when the ratio of VD to VT is relatively small. Say 6 times, 2.5 volt is the VDD, and threshold volt is around 0.4 volt. If this is the case, ratio is too high, then it is difficult to move the Vm to 1.5 volt, for example. Takes ratio WP by WN 11, and 11 is quite large value. Okay, area wise it is not good. Further increase are prohibitively expensive. Observe the things in semi-log plot is talking about that plot. Which plot? This plot. So increasing VM is going to take, see here it is 10 times WP by WN is 10. You further increase, your VM is not increasing too much. Anyway, going further, some noise margin formulation. Our topic now, earlier we are discussing switching threshold. Now we are going to start another topic, which is noise margin formulation. So this all you have taken considered BDD is equal to 1 volt B in. If B in is we are actually explaining this current spike here, and it is nothing but we have I think discussed, that is 3 type of power is there. One is what? Tell me. P dynamic, and second one is P static. Another one is there. Tell me somebody. As well.
Leakage. Leakage.
Static is leakage only. This is only leakage or whole power. In case of SRAM cell, we call whole power also. But third one is what? P direct path, DP, or it can be also said P short circuit. Okay.
Yes, sir.
Short circuit. Did I say or not in our discussion, earlier discussion? Tell me.
Yes, sir.
This we have discussed. So here, how this spike, I mean current actually ideally speaking, either pull down or pull up network is on. So ideally there is no static power or leakage power. Okay, there is no leakage current rather. Only dynamic power when your CL is getting charged or discharged. But when the transition is occurring, input is rising and hence output is gradually falling. During that time, what may happen? You can, I think I have discussed, but some of the students led joint or not present. So I'll once again tell that suppose threshold voltage of the MOSFETs is VTN equals to VTP equals to mod of 0.4. Means for VTN 0.4 volt or VTP minus 0.4 volt. Supply voltage taken as 1 volt. Okay. Suppose input is having some rise time. You know that it can never be a square shaped input. Okay, because the signal is coming from so many other gates, and there will be always rise time and fall time. Charging time is required certain time because of the RC delay. So suppose it is rising, input is rising from 0 and it has raised up to 0.4 volt. When it is point V is 0.4 volt, what will happen to the MOSFET? The NMOSFET will start conducting, right? It will start conducting. And what is the state of PMOSFET? When it was 0, PMOSFET was on? Yes or no? It was off, but now the V in is exceeding 0.4 volt. So this will start conducting. What is the status of PMOSFET in that point? Suppose it is 0.41 volt or so, or 0.42 volt. Tell somebody what is the state of PMOSFET. you know, on in MOSFET has started conducting. What is the state of the MOSFET? It is on or off. It is conducting or non-conducting. Somebody say, Harshvardhan, Harsh Tripathi, are you there? Harsh Tripathi, Kartik Rai, Himanshu Shogra, Prem Prabhat, Pramanik. Okay. Prajwal,
Yes, sir.
tell what is the status of the MOSFET here when input
It,
voltage B in is rising from 0 and it is now say 0.41 volt.
it will also conduct, sir.
Hmm?
It will also conduct because VGS
It is
once
also
if it is
conductive.
less than -4.
It is also conductive because we know the MOSFET will be on P MOSFET on state of P MOSFET on P MOSFET. Condition is what? VGS should be less than VTP. VGS is what? Say I am taking 0.4. VG is 0.4 and VS is what?
1.
1. Should if it is less than VTP minus 0.4, so it is true because it is 0.6 volt. Yes or no? 0.6 less than 0.4, it is true. This case is true, so this is also on, and it will be on. Say it is input is raising, and it is raised up to 0.6 till this point. If I say this is a time axis, if I say this is time, so from this time to this time, this time to this time, you're uh, taking some time. 0.4 volt to it is having some rise time. So to raise input signal from zero point 0.4 volt to 0.6 volt, whatever time is required, during that time both the MOSFETs are on. Okay, after that the MOSFET will go off. So there will be direct connection from in MOSFET, sorry, VDD to ground, and current spike will be generated like this. Okay, and that happens when MOSFET's output node is switching or input is also making transitions. Because of that, the direct path current or short circuit path current will be there, and hence short circuit power or direct path power will be consumed. Anyway, let me go further. See, in the VTC, 5 points are shown. One is one region, another region, and this is another region, D and E. And during in each region, MOSFETs are changing from certain region operation to another region operation. And that is shown here in this plot. When V in greater than equals to 0 less than VTN, then P MOSFET is in linear region and N MOSFET is cut off and V out equals to VDD. Then B in greater than equals to VTN less than VD by 2, P MOSFET is linear and N MOSFET is in saturated state. Remember that when in this, if I plot a say B in equals to B out plot, B in equals to B out plot, and if it is intersecting here, VM is somewhere here, VM is say VD by 2. I don't know what is VD, but say VD by 2. So when VM equals to VD by 2, what is the state of the MOSFETs? I mean, region operation of MOSFET. That may be a question. So I'm leaving. This is quite informative. Understand and try to prepare yourself for quiz questions. So I can ask a question the state the region of operation of the MOSFETs when Bm equals to Vd by 2. What will be the answer? Can anybody say?
Both will be in saturation region.
Both will be in saturation region. So that is what repeated here also. I am skipping. Okay. The typical VDC of realistic NMOS inverter is shown here. Here it is gain the V out by dV in is -1. Here is also dV out by dV in -1. Okay. This point, at this point, this is called VIL and this point is called VIH. Using these two, we find out the noise margin. V out, the V out is say dropping and due to change in V in. So here this point is denoted by the input voltage here is called VIL and this one VIH. Based on this, noise margin is decided. For very low input voltage levels, the V out voltage V out and the output voltage V out is equal to high value, that is VOH, output high voltage. As V increases, the driver transistor, driver means in MOSFET, driver starts conducting a certain drain current and the output voltage eventually starts to decrease, as you can see here. The output voltage levels does not drop abruptly, such as assumed in ideal inverter. Normally, ideally, you will say this kind of VTC. No, it doesn't happen actually. There is some slanting there. But rather, gradually with a finite slope. Two important points on the VTC are when the slope becomes -1, that is dV out by d V in equals to -1. The smaller V in satisfying this condition means gain equals to -1 is called VIL, input low voltage, and larger V in satisfying this condition is called, this is V in x-axis is V in. Satisfying this condition is called the VIH, input high voltage. VIL, VIH can be found using the unity gain points. This is unity gain points, both from the region B. This is region B and this is region D. Earlier, A was also denoted, C was also denoted, okay, and E was also denoted. This was A, this was C, this was E, okay. So can be found using the unity gain points from the region B or D of inverter VTC. As V further increases, V out continues to drop and ultimately equals to VOL, output low voltage, when V in equals to VOH. V in equals to VOH here. The inverter threshold voltage VTH or VM, it is some books denote VM as VTH. In Rabway, you find this one in your textbook. Okay, mostly I'll be using this VM because VTH is used for other purposes. So this inverter threshold voltage is the transition point on the inverter voltage defined as P in equals to V out. A total 5 critical voltages are denoted here, like VOL, VOH, VIL, VIH, and VTH or VM to characterize the VTC of the inverter. So noise margin definitions, how will you define it? Noise margin is a parameter that allows us to determine the allowable noise voltage on the input of a gate so that the output will not be affected. There are two parameters to specify noise margin or noise immunity. The low noise margin denoted by NML and high noise margin NMH. Okay. With reference to this figure of wastage, NML is defined as the difference in magnitude between the low output voltage of the driving gate and the maximum input low voltage recognized by the driven gate. Thus, NML equals to VIL max minus VOL max. Is it understood? And it is shown with some example also. Is it understood? See the diagram and try to understand, tell what is NML and what is NMH. One gate inverter say driving the another one. Okay, and all I have mentioned to make you understand. Tell me whether you are understanding or not. What is the two noise margins, NML, other one is NMH. With some values I have explained. This is showing the output profile of this gate, first gate. Output profile means VOH is shown here, not VDD, but little less than this one. This could be VDD, and if VOH or output voltage is up to this point, still it can be considered as high. Okay, ideally should be the out should be 1 volt in case of 1 volt system and 0. Okay, the out, but it may be also considered high if it is lying from 1 volt to some low voltage lower than 1 volt. VOH, VOH mean. This is minimum output voltage, which can be considered as high. And here VOL max is the maximum voltage, which can be considered as low. 0 is low, everybody knows, but yes, how much above 0 volt can be considered low, that is VOL max. Okay, and here on the right side inverter, you have the input profile. Logical low input profile. See, it is said that up to this value, say 300 millivolt, I have written here 300 millivolt. If any input coming from this side, input side, if it is even 300 millivolt, that is VIL max, up to that value it can be considered as low input because its threshold voltage may be 0.4 volt or so. So the pull-on MOSFET will not be on. And here input profile here is input characteristic of this inverter is from here to here. This value can be considered as high input, and see the margin is from here to here. NMH is the difference between VOH mean and VIH mean. So there is always margin provided here. Understood? This example, VIL max is 300 I have taken, this one, and VOL max is taken as 200 millivolt. So 100 millivolt is the noise margin. Which noise margin? That is NML. If you consider the NMH, what I have considered here is, this is VDD means 1000 millivolt proper VDD, and viewer H mean taken as 800 millivolt. Okay, so and here in the input profile side of the second inverter, VIH mean is given as 700 millivolt. Even 700 millivolt mm, input coming from this one can be considered as high. So, so NMH here, VOH minus VOH mean minus VIH mean is 800 minus 700, that is 100 millivolt, is the in this case is the noise margin. Understood? You can expect questions on this. You have studied in DST, I am sure. Rajwal, have you studied or not?
Yes, sir.
So
We
it
saw this
may
for
not be.
CMOS, TTL, and
Yes,
VCA.
CMOS, TTL, etc. I have studied, and same thing we are repeating. So you may be aware of it, so you can go fast. Same definitions are given here, and hence I'll not um, spend time. Okay, these all are known, so I am keeping very going fast. Let us consider this circuit consisting of three cascaded identical inverters. Okay, we are going to discuss this thing from here. The ability of an inverter to interpret an input signal within a voltage range as either a logic 0 or as a logic 1 allows digital circuits to operate with a certain tolerance to external signal perturbations. This tolerance to variations in the signal level is especially valuable in environments in which circuit noise can significantly corrupt the signal. Not necessary that you will be getting input to your circuit as square wave and very good high, very good low. No. Here, the circuit noise corresponds to unwanted signals that are coupled to some part of the circuit from neighboring lines, usually interconnection lines. We'll be spending some times on second module on this. By capacitive or inductive coupling. Capacitive and inductive coupling is the main reason for noise. Okay, creation of noise in a circuit from the outside system. The result of this interference is that the signal level at one end of an interconnection line may be significantly different from the signal level at the other end. Long interconnect is there, so it may be different. See that. Let us consider this circuit consisting of the three cascade identical inverters as shown in this figure. The input voltage of the first inverter is equal to VOH. You know, input signal here is VOH. And what is VOH? The value of the signal here, which can be considered as high. It may not be up to VDD, but some less value than VDD, but still it is high. Okay, a logic one, you can say. Okay, by definition, the output voltage of the first inverter will be equal to VOL. It should be VOL. Okay, and value of VOL may be zero ideally, but it may be little higher than zero, corresponding to logic level 0. This output signal is getting transmitted to the, say this one is not ideal 0 but 0.2 volt, for example. Okay, this output signal is getting transmitted to the next inverter input through an interconnect line. This is the interconnect line, okay, copper wire, for example, or aluminum wire, which may be metal or polysilicon. We are connecting the two gates. One's output is connected to the input of the other one. Since on-chip interconnects are generally prone to signal noise, the output signal of the first inverter will be disturbed during the transmission. Okay, see that interconnect line is changed. Suppose some positive spike has come here, and that value is 0.3 volt. I have assumed here to explain 0.3 volt positive spike has come. Okay, and hence the voltage over here is 0.5 volt. Okay, now we know that input profile of this gate is VIL max is 300 millivolt. Then what will happen? This voltage 0.5 volt may not be considered anymore, cannot be considered as low. It could be considered low if its value was 300 millivolt, 0.3 volt. But now it is difficult. If that much noise is coming, then it could tolerate if the noise was within or less than 100 millivolt. We have seen in the previous example here. Yes, this one. This one, if 100 millivolt, then it was okay. But for now, it is the noise has come little more. Okay, so this cannot be considered as low but high. So your further circuits will get bad output and bad input. Okay, or you can say due to noise, your circuit will start malfunctioning. Is it understood? Yes or no? Consequently, the voltage level at the input of the second inverter will be either larger or smaller than VOL. If the input voltage of the second inverter is smaller than VOL, this signal will be interpreted correctly as a logic 0 input by the second inverter. If due to noise VOL greater than VIL, then second inverter may not interpret correctly. Okay, here thus VIL is the maximum allowable voltage at the input of the second inverter, which is low enough to ensure a logic 1 output. Logic 1 output here should be 1. Okay, because this was low. Okay, this was low. But because of noise, if noise comes is 0.3 volt, then it may be low. Understood? Now consider the signal transmission from the output of the second inverter. Yes.
Sir, we have a class right now. Can we see this in the next class?
Okay. So you study this noise margin case because it is all known, and hence these equations are required to be understood how the noise margin can be computed. Okay. So if you study, okay, but nobody is attending the classes, so how you will study, I don't know. Anyway, and the next class. Coming Sunday, we'll finish it and conduct the exam.